So let's start the afternoon session. It is my pleasure to introduce my colleague, Francesca Toni. Francesca is a professor at the Department of Computing at Imperial College. She's a professor in computational logic and the Royal Academy of Engineering JP Morgan Research Chair. She's the founder and leader of the computational logic and argumentation research. She has done seminal work in this area, and she holds an ERC advanced grant, also in the area, so congratulations. Okay. And so today we are going to hear about interactive explanations for contestable AI. Please, Francesca, go ahead.
Thanks a lot, Roberto. The microphone works? Yeah, good. I'm going to tell you a little bit of, I'm going to give you a bit of information about the kind of research I do, but first I'm going to put it into a broader context, and in particular provide some motivation as to why I'm doing it. So in the first part of the talk, which consists of 3 parts, in the first part I will discuss whether we can trust AI and motivate why, in my mind, we need explainable and contestable AI, rather than the kind of AI that we are currently doing. I will then give you a little bit of background on the technology that we use to provide AI that is explainable and contestable. And that's based on what we call computational argumentation, which basically is at the intersection of 3 areas in AI. Knowledge representation and reasoning, which has its roots in symbolic AI, multi-agent systems, as well as machine learning, and in particular natural language processing within it. In the third part, I will give you some of the solutions that we are developing using computational argumentation towards explainability and contestability for AI. Okay, so let's start with the question, which to me is a big motivation. Can we actually trust AI? And I guess, many of you probably like me will not be sure that we can. And this is especially because nowadays AI is mostly opaque. We have these very large systems that are built on very intricate models, and we don't really understand what they're doing, where they're getting the information, and why they draw the conclusions they draw. And this is especially worrying because we know that AI is prone to a bunch of problems. For example, it may identify in data artifacts, so draw maybe the right conclusions for the wrong reasons, such as backgrounds rather than content of road signs. It may be manipulated, as it happens if you put stickers on road signs. Some AI may come to the wrong conclusion. It may have biases because the data from which it's built may have biases too. So, for example, you may get completely different outputs for individuals which are identical, other than attributes that should not play a role in the output at all. And also, as we very well know these days, this is a very popular drawback of AI, it may hallucinate. So it may actually come up with wrong information, as it happened. This is an example I drew from a legal case where lawyers used ChatGPT to prepare their case, and they used wrong information provided by ChatGPT. So for all these reasons, I think it's very hard to say, yes, we can trust AI. And because of others that, like me, think we can't quite trust AI, there has been a lot of movement, a lot of energy around trying to find ways to mitigate these problems and provide AI that is more trustworthy. And one thing that is advocated by many is explainability. So explainability is studied widely within the AI landscape by researchers, but is also strongly advocated by regulators and by ethics frameworks. Here I'm taking two examples. One is from GDPR, which is law in the UK since 2018, which says explicitly that we should be able to obtain an explanation so the decisions reached by machines. So an explanation is required. So those of us who are developing AI that does not come up with explanations is in breach of this legislation. Also, I have here put an example of a principle from one of the many frameworks for ethical AI, that's by the OECD, that has one principle specifically on transparency and explainability. So explainability is advocated by very many as one of the paths towards creating AI that is more trustworthy. In reality, explainability is not at all a new thing in AI. Explainability has been a requirement for AI forever. And here I'm just putting some very old slides about expert systems that were so popular in AI in the 70s and 80s. And they were completely transparent. They were basically sets of rules that were human designed. But still, even at that time, there was a big drive towards explaining them. Because when the human is in the picture, you want to be able to empower the human to make sense of what the machine is doing. So, very hot topic now, as it has been forever throughout the history of AI. Okay, so if we agree that AI needs explaining, no matter what the AI is, transparent or opaque, we need then to answer a question as to what kind of explanations we want to take out from AI so that we can understand what it does. And there are very many approaches in the literature, but there are also calls from within the AI literature to really put the human at the center of the question of what explanations should be. And in particular, Tim Miller famously looked at the social science literature and advocated that explainability in AI should really take the social sciences into account, not just AI itself and human-computer interaction, but also adopt solutions that humans adopt when they explain to each other. So looking at how humans explain to each other can serve as a useful starting point for explanations in AI. And in particular, Tim Miller advocated that the explanations should have four important features when applied to AI. They should be contrastive. So when we explain to each other, we don't just say why something, we say why something rather than something else. That's something that we kind of all do. Explanations need to be selected. We rarely want the full explanation that takes into account all the information possible. We want something to the point. So explanations need to be selected. Another important point is that explanations are social. They need to factor in the interactions between the explainer and the explainee, and they need to be able to convey information across. So both, all parties involved in the explanatory process need to be factored in when building explanations. And lastly, something that I will not address kind of directly, but it's an interesting point, probabilities probably don't matter when you build explanations. The people are more interested in causal relations than in numbers. So the kind of systems that I'm building for explainability are definitely satisfying the three bullet points and mostly the last one as well. Okay, so that's one important aspect. When we build explanations, we need to take into account these properties. But is that it? Is that the end of the story for trustworthy AI? In reality, that's not the end of the story. There is another important factor that we need to take into account for trustworthiness and alongside explanations. And that is the need for AI to be contestable. And the very same quotes that I've used to motivate explainability really also motivate contestability for AI. So you can see here that in this doesn't work, in this quote, that it's not just important to obtain explanation, it's also important to be able to challenge the decision by the AI or by the automated system. Again, this is law. Are we doing this? We are not quite doing this. But it's in the law. And similarly, if you look at more or less all frameworks for ethical AI, again, they are raising this point. You need to be able to challenge the outcome of AI. And this challenging the outcome is what I call contestability. And that's something that we really need to factor in when building AI. So the kind of AI that I think we are after is contestable AI, which can be abstractly seen in this way. So AI needs to be typically being equipped with a model. For example, a convolutional neural network or a transformer-based architecture or whatever. For it to be kind of contestable, needs to be able to provide an explanation for what it does, because otherwise the contestability is very limited. You can only contest the output, and that's it. You cannot really contest what the machine is doing. So the machine needs to come with an explanation for full contestability to be achievable. And also, if the contestation happens by a contester, for example, a human, because of some reason, some kind of grounds for contestation, the machine needs to be able to redress the issues raised and change, basically. That's what contestability means, the ability to change in reaction to a contestation based on some grounds. So I see these components as very important, that an explainer and the ability to redress issues characterize the AI that is being contested following ground contestation by the contester. And of course, here we have the AI being contested and the human contesting, but nobody stops us from the AI contesting the human, or from two AIs contesting each other. So this is a quite general abstract view that accommodates all these instances. No matter who is contesting and who is being contested, you also need to have the ability to interact. Without that ability, no contestability can happen. So what I'm going to focus on in this talk is the viewpoint of the contested AI and see how we can achieve this vision of kind of contestability by means of, supported by explanations in some settings. Let's start by asking ourselves the question as to what explanation, what the E component of the model should be like. And of course, we can look out there in the literature, and there is one particular form of explanation, which is widely studied in AI, that could be and is advocated for contestability, and that's counterfactual explanations. So let me give you here, I'm giving you a very simple illustration in a specific setting where we have a machine learning model, for example, that can predict whether a mortgage application is granted or denied. And suppose we have an applicant whose mortgage application is denied. A counterfactual explanation is another applicant, real or fictitious, that has very similar characteristics, as close as possible, but whose application was approved. So it's a data point very similar to the input one, but with a different outcome. And that's what a counterfactual explanation is, and you can see why this is an explanation, because if you look at the difference between the two, you can see what is motivating the outcome. You could say that the mortgage application was denied because of career breaks, because had there been no career breaks, the mortgage application would have been approved. So this is a conventional kind of explanation. There are lots of ways to do it, lots of ways to determine what similar means, etc. And lots of properties that are studied for this, including by my group. And this is advocated by some as a clear form, as offering a clear path towards contestability. Indeed, counterfactual explanations are also called algorithmic recurs, kind of in the literature. And there are a form of contestability, but very, very limited, because they only allow the input to change in order to get a different output. They don't allow the actual model to change at all. And now what happens if you have a situation like this, that you use a counterfactual explanation to justify why a certain outcome, the mortgage application being denied, happened, but you want to contest the model, not the, the input, because you cannot stop having had career breaks. That's not something you can change. What if you say, my career breaks were due to maternity leaves? Are you not gender biased? I mean, this is the kind of contestability we want to be able to support if we want to be able to trust the AI. And that's not something that counterfactual explanations can support at all. So in my view, what we need to do is we need to rethink explanations, but more generally, we need to rethink AI. And I'm not the only one to hint at the fact that we need to rethink AI. There is, famously, Stuart Russell that said that we need to have AI that is able to accept correction. For example, admit that, yes, there is a bias in my model. I am penalizing women who take maternity leaves, and I need to change the model. So we need to be able to correct the model. But I think more broadly, we don't just need to rethink artificial intelligence. We need to rethink intelligence. And in particular, we can appeal to social scientists again, who are, for example, advocating that we develop intelligence not to take the best decisions at all, but in order to argue with each other. This is an evolutionary understanding of intelligence. We became intelligent with the ability to reason because so that we could argue with each other, because arguing with each other would help us persuade and get a team of people killing a Mahmoud rather than being alone or defending ourselves against a pack of lions. So in particular, this line of work recommends that reasoning needs to be, and intelligence more broadly, needs to be understood in the context of exchanges of arguments and counter-arguments between humans. And that's the abstraction, if you like, that I go for in my work. And I do so by using techniques, developing and using techniques from what is called computational argumentation. So I'm going to give you a very high-level view of what computational argumentation is, and in particular, the kind of computational argumentation that I use in this talk. Now, computational argumentation is a very theoretical field with lots of theorems, lots of definitions, computational complexity, algorithms, soundness, completeness, you name it. I'm going to keep it really high level here and try to give you an intuition. So, in a nutshell, computational argumentation is about identifying frameworks which are somewhat capturing abstractly debates. Possibly the easiest to grasp frameworks are structured argumentation frameworks and abstract argumentation frameworks. Structured argumentation frameworks see arguments as deductions or conclusions or claims from premises. For example, we may have an argument that says that a certain movie is recommended because the acting in the movie is great. That's an argument, okay? Arguments can disagree with each other. For example, an argument that the acting in that movie is not great because some actor is bad in it is another argument that disagrees with the first one. In jargon, we say it attacks it, and should be factored in when deciding or not whether to watch that movie. And here, for simplicity, it's a simple debate, but it's a debate nonetheless. There may be some other argument. Somebody says, what are you talking about? That actor is not in the movie, so it cannot be actually bad in it. So that's an argument attacking the second argument, which attacks the first argument. So argumentation frameworks, as I said, are abstractions of debates, and the possible abstraction in structured argumentation is of this form. And we get these frameworks, for example, from rules, from text, from data, etc., from various sources. They are abstractions, okay? An even simpler variant, which, however, is, to me is easier to understand after this, is what we call abstract argumentation, which basically boils down to graphs. An abstract argumentation framework is a graph. The nodes of the graph are arguments, and we don't care what they are. They are kind of opaque. They're just nodes of a graph. And the edges represent attack. You can see that this is an abstraction of the previous type, and indeed, you can obtain abstract argumentation frameworks from structured ones, and again, from various other sources, including from games, from schedules, from text, from data, etc. So there are various sources for these frameworks. So these are just examples, and independently of which one you go for, you need to decide what you do with them, right? They are representations, but you want to use them. Typically, we argue because we want to reach a conclusion. So reaching a conclusion here amounts to determining which arguments are accepted dialectically. So are we going to watch the movie or not? Should the movie be recommended? Does that argument stand against criticism? So what we do is we develop semantics, which are basically recipes for determining which arguments are accepted in these debates. And in this very simple case, we would have that the black argument is accepted because nobody disagrees with it, so it's in. Dialectically is as strong as it gets. The purple one is rejected because it's attacked by an accepted argument. And the blue one, about the movie being recommended, is accepted because it's attacked, but the only attacker is out, is rejected. So it is defended against that attack from an accepted argument. I'm just trying to give you the kind of intuition. So that's one line of work, and we use some of these for developing expandable models built from data, as I will show you if I have time. Another line of work that we use widely to explain existing methods, such as neural networks, is what we call bipolar argumentation. In bipolar argumentation frameworks, in addition to attack, we also have another dialectical relationship, which is quite common. We don't just disagree with each other, we also agree with each other. So we call this support. So again, they're graphs, but with two types of edges. The attack and the support. And these kind of frameworks can be, again, equipped with extension-based semantics that say which arguments are accepted or not. But if you have numerical information about the arguments, you can do more, and you can equip them with what we call gradual semantics. So the numerical information in this particular case, the numbers between 0 and 1 inside the actual arguments may represent how much we trust the source of the argument, or how well constructed is the argument in the node, or whether the argument is about something we care, or the bias of the neuron that the argument represents, as is the case when we understand neural networks as argumentation frameworks. No matter what, we have this number, we call it the intrinsic strength, the strength of the argument prior to debate. So if you ignore the debate, how strong are those arguments? We can then define gradual semantics, and we have very many of them we studied. Here I'm illustrating what one such semantics does. Unattacked and unsupported arguments have as their dialectical strength their intrinsic strength. So the black and the brown arguments stick to that same strength. So the dialectical strength is in the box outside. Attacked arguments have their intrinsic strength decreased. Arguments that are both attacked and supported have their strength decreased if the supporters are stronger than the attackers, and increased if the supporters are stronger than the attackers, and decreased if the attackers are stronger than the supporters. We don't need to understand the details. I just want to give you a feeling of what's happening. Okay, so these are all frameworks we use for explainability and for contestability, as I hope I'll have time to show you. What's interesting is that, these are all transparent representations. But as I told you up front, interpretability does not equate with explainability. You also need to explain interpretable models. And argumentation frameworks come with lots of explanation formats. The first one, I'm not going to give details. I just want to mention that you can determine the attribute, how much each argument or dialectical relation contributes to an output, and you can determine counterfactual explanations for argumentation frameworks too. But importantly, you can build interactive explanations very naturally from argumentation frameworks, I guess for obvious reasons. I'm giving you here an example. It's an example where you have a recommended system on the left that recommends a certain movie, and in its mind has some reason, has built some knowledge, what we call is an argumentation framework for their conclusion. And we have a human that received the recommendation but is not convinced because the human has its own knowledge and may have doubts, may want to question, may want to contest the recommended system. I don't agree with with what you are recommending me because I heard that the actor A is poor in it and the director in it is poor. I mean, I've read it in newspapers. So Rotten Tomatoes said that. So the human has some some knowledge. Now the human doubting what the recommended system is doing amounts to contesting it and asking for information. And the recommended system can provide this information, but put forward having the human put forward additional information may actually say, you're right. Maybe the movie is not that great after all. I did not know about that information. I have partial knowledge. I am not perfect, and I'm happy to kind of give in. So basically, what we can do with argumentation, if we manage to see the machine and the human as argumentation frameworks, then we can naturally get them to talk and to at least convey information towards contestability. And of course, we study lots of properties, the fact that these exchanges show, demonstrate when consensus was achieved or not, etc. And this is a very important aspect of argumentation that I'm not stressing here. We study lots of properties that are human appealing, that we believe are important towards explainability when humans are in the loop. Okay, so this is the kind of brief introduction to computational argumentation I want to give you. But I want to argue before I give you the actual solutions why computational argumentation, I believe, is important for contestable AI. Of course, there is a personal reason that I like it and I work on it, but that's not why I think it is important. So computational argumentation has some very crucial features towards contestability. It's what we call in jargon non-monotonic. And there are lots of talks about using symbolic forms of logic, etc., to provide explanations. But many of these logics, starting from classical logic, are monotonic, which basically means the more information you give to them, the more conclusions they draw. But contestability is all about withdrawing conclusions. You want to change things. So you can't use a monotonic logic at all. Now, argumentation is by definition non-monotonic. So you can add more information and it's perfectly happy with withdrawing conclusions, as it happened with the movie recommender. So that's an important feature of computational argumentation as a representation framework. Also, as I just shown you, it's equipped with a variety of explainability formats that can turn out useful in various application settings, and it lends itself well to interactivity, again, as I just shown you. So the one real question that we need to answer is where it is sufficiently abstract to provide kind of counterparts of things we want to explain. So can we distill argumentation frameworks from models that are opaque or otherwise, and that we want to explain and contest? This is the big question here, because all the other boxes are ticked. But of course, at the moment, it's just floating in the air, right? Unless we connect it to the actual models we want to explain and contest, is not much use. So what I'm going to try and show you that we can distill argumentation frameworks from models when we want to explain and contest them. And we can use argumentation to define interpretable models themselves that are explainable and contestable. OK, so I'm going to start. Can somebody tell me the time? There is no clock I can see here.
You have 20 minutes.
OK, good. Thanks. So the first form of what we call argumentative explainable AI is one where we distill argumentation frameworks post hoc from models that are non-argumentative. So basically, we approximate these models by means of argumentation frameworks, and then we use these argumentation frameworks to explain them. Of course, this requires, for it to work, that these frameworks are faithful. Okay, we want to distill frameworks from the model we want to explain, but they need to be faithful to the model being explained. Otherwise, what are we explaining? So faithfulness is a big question. Another question is, what kind of format of explanation do we need to empower contestability? And also, how can we support redress following contestability? So how can we update the models that are being explained argumentatively if we get criticism from a human user as to the fact that they need to be changed? So these are all question marks, and I'm going to try to address them in the case of some neural classifiers we have been working on. So let's start with multi-layer perceptrons. These are the simplest kind of neural models, so we started from them. You may be surprised by these, but multi-layer perceptrons are argumentation frameworks. They are equivalent. So you can take a multi-layer perceptron and see the neurons within the multi-layer perceptron as arguments, and the connections between, from one layer to the next as other attacks or supports, depending on what what the learned weights are, whether they're positive or negative, and the bias corresponds to the intrinsic strength. So this has been proven formally. A multi-layer perceptron is a weighted argumentation framework, bipolar, attack and support. OK, that's interesting, you may say, but how does that help us? The argumentation framework is as big as the multi-layer perceptron, so how are we addressing the problem? And indeed, we are not, unless we do, we go one step further. And the one step further that we are kind of carrying out is one of sparsification. So we can take a big multi-layer perceptron, as big as it needs to be, and we have developed methods for sparsifying it by clustering neurons so that each argument in the argumentation framework we obtain is a cluster of neurons, and then use the existing correspondence to map them into a weighted, quantified bipolar argumentation framework that we use as the basis of explanation. But of course, for it to provide useful explanations, we need to make sure it is faithful to the original multi-layer perceptron, and especially given that sometimes we want to sparsify a lot to get a a much smaller variant that is cognitively tractable to humans. So what we do is consider various forms of faithfulness. Input-output faithfulness is the sparsified version of the MLP, providing the same outputs, given the same inputs as the original multi-layer perceptron. But we also look at structural faithfulness. So do they correspond at every step of the reasoning? Because you can see a multi-layer perceptron as performing reasoning, carrying reasoning through. So we have various experiments in which we compare with various methods. For example, Hessian-aware pruning is a standard method for shrinking a multi-layer perceptron, and you can see that we are much more faithful. Here we are measuring unfaithfulness, so the lower the better. We manage to be much more faithful than these competing methods, and there are various types. types of explanation we can draw, global and local, and these are just examples of the kind of experiments. But we can use these methods to provide explanations for multi-layer perceptron, which are much more manageable for humans. For example, we can take a multi-layer perceptron built on the COMPASS dataset, which is well known for being biased and giving rise to biased models, and we can decide how much we want to sparsify the MLP. One hidden layer only, and we can see that we can compress it 20% or 80% or 85%, and we get an argumentation framework which is much more manageable than the original one for the given MLP. And if we can make sense of the clusters of neurons in the middle, may also provide useful information. And so we do that by various methods. For example, we build word clouds from the clusters of neurons by looking at which training data are activating the clusters to provide a high-level vision. So basically, at the end of the day, we take a multi-layer perceptron, which is big, and we get something small, such as this explanation here, that users can leverage. So we have done this also with images, together with prototypical-based learning, but I'm not talking about that. So that's one first approach of how to build explanations for neural classifiers, leveraging on argumentation frameworks distilled from the classifiers. Another approach is, in this case for images, is just using a quantized counterpart of an image classifier built with a convolutional neural network, for example, and leveraging on the quantized features to build debates between two fictional players that are explaining what the classifier thinks by debating with each other. So in this case, we have two different sides. I mean, these are the gray and black little faces that can explain why a certain image was classified one way or another, as a cat in this case, by pointing to the quantized features in the classifier within a debate where the two players, one arguing for the classification and one arguing against, interact. So this is somewhat a way to reflect the uncertainty of the classifier by a debate whereby the players are trained in a reinforcement learning manner. So that's another line of work that uses very flat argumentation frameworks where the two players just argue for or against the classification to explain what the classifier is doing. And again, we check that these are faithful in many ways, and we do so in comparison with existing methods for explaining image classifiers. The final example I want to give you for neural classifiers includes also the contestability angle, because so far all I've shown you is how argumentative abstractions can help explain neural classifiers, but can they facilitate contestability? So here I'm giving you an example with text classification. Again, we have done this. This was in the pre-transformer era, or when transformers were not as widely used. So this is work we have done using a convolutional neural network again for text classification. So you are given an input. Here is shown on the left, and the machine computes an output. For example, that this text is about business, but maybe not with a high confidence, just 65%. So what we do again, we can leverage on ways to distill an argumentation framework from this kind of network where the convolutional filters now become arguments, as well as the input and output become arguments. And we can then study again the faithfulness. I don't want to go into details, but we can take these argumentation frameworks, which again are interpretable but they're not explainable, and we can draw human-oriented explanation from them by, again, turning the filters, which are the obscure, opaque arguments into word clouds by using the training examples and activations of the filters by then. And we can interact with the explanation by, for example, checking why is this filter, what is this filter doing, the filter here on the right. And the filter is attacking the prediction. There is a red arrow. Red arrow means attack. It's attacking the prediction and is supported by those three input words, which are arguments in our frameworks. And you can see that actually the model is not a bad model. It's a good model. It's right that that filter should attack business, because it's not about business, it's more about defense, right? So you can interact with the explanation and gain some confidence that this model is trustworthy because it kind of reasons in the right way. It tells you that it's 65% confident that a certain output is, that the text is business, but it tells you why. It tells you, look, this filter, I think that this filter is activated, and this goes against that prediction. So this is the kind of interaction you can have, and we have used precisely this kind of view of convolutional neural network to support redress if contestability happens, for example, because of bias. So we have we achieve contestability by a process of fine-tuning. Should one of these filters not do the correct thing, should it attack for the wrong reasons or support for the wrong reasons, we can get humans to say, I don't agree with that. You shouldn't use this filter. And the technique that we developed is about fine-tuning the model by switching off, basically, or de-emphasizing those arguments that should not play a role. And we have shown that by doing that, we can actually decrease the bias of models in a way that is empowered by the contestability. Okay. So that's all I wanted to tell you about the neural classifier. There is more work we are doing in this spectrum, but this is just hopefully a taster. I'm happy to take questions or discuss later on. The second line of work I wanted to tell you to conclude is one that instead of distilling argumentation frameworks from models, builds models from scratch that are argumentative. And then construct explanations and contestation from these models. So here we have a native use of argumentation frameworks, and we are developing several models along this, this direction, where the model is built on an argumentation framework. Let me give you, of course, here the question is not faithfulness, because, by definition, the model is faithful. The question is performance. How well is this argumentation-based model performing against the state of the art, which uses neural classifiers and other techniques? So here, really, we need to check that the method is competitive. Okay, let me give you 3 examples, if I have the time. So the first is what we call data-empowered argumentation, where we basically have positive and negative examples of a concept. For example, the examples may be images, like in this case. And we don't know what the concept is, but we want to learn it, to extract it. So what we can do is we tend to start with this is all about debating, right? So we need to have a beginning of a debate, how we start the debate. And for this, we use what we call a default argument, which is, if you know nothing about the image, what conclusion would you draw? In this particular case, for the sake of illustration, if I know nothing about the image, I would say I draw the conclusion plus, which is one of the 2 classes I'm considering. So this is the beginning of our debate. And then what I'm going to do is I want to, I can take all these data points, the existing ones, the positive and negative examples, and this default argument, and construct an argumentation framework. How? Well, basically, there is a disagreement built into a data set with 2 classes, and they are labeled by different classes, so they disagree. But there is more to it. We need also to take into account the fact that you can't have everything attacking everything else with a different opinion. That wouldn't be a very interesting debate. So we enforce a notion of specificity or a partial order on the data point, and sometimes we learn this. that allows us to create more, slimmer and more interesting debate. In this particular case, what happens is that the image where there is a blue triangle which is labeled as negative, attacks the default argument, which is, if you know nothing, it's a positive concept. And in turn, the image with the blue triangle is attacked by the positive image, which has a blue triangle, but also some red on green shades. It's a silly example that stays on one slide. I hope you'll forgive me. So basically, a labeled data set is an abstract argumentation framework. Arguments are data points, and disagreement is defined as I told you. Then, of course, if you want to predict what's the outcome for an image you don't know the outcome, you don't have a label for, you can actually throw it in the debate and say, let it attack everything that is irrelevant to it, because it has features this image doesn't have. And then all you have is a debate. You can analyze it with one of the semantics. And you can see, did the default argument stand against criticism? Did it win the debate? Is it acceptable? If it's acceptable, the prediction is the default one. That's one method we developed, and you may say, that is never going to work. What the hell is happening here? In reality, it's what we are using, for example, in collaboration with neuro-oncologists at the Charing Cross Hospital. They have data collected with the brainware clinical trial with a wristwatch for patients with brain cancer. And it's not a lot of data, so standard models, neural models cannot be applied, basically. We have applied the variant of what I just told you, and you can see that the performances, there are various ways to instantiate it, etc. The performances are very competitive against similarly transparent, applicable models in this setting. So I guess what's interesting is that we don't use any statistics whatsoever. We just use reasoning with these data points in order to draw conclusions, and this seems to be working well in some cases. And we go further than that by using a structured argumentation framework where the arguments have components and not just nodes in a graph. And without going into details, we can similarly draw conclusions, but we can also inject background knowledge into the learning processing. We've actually used that to perform image classification in conjunction with lot attention for feature engineering and with kind of competitive performances. So what's interesting about these methods is that they allow to combine dealing with the two forms of uncertainty which are underpinning most machine learning, the aleatoric one and the epistemic one, in two different ways. The aleatoric one is dealt with by the neural methods, and the epistemic one is dealt with argumentatively by having multiple interpretations of the same data. Do I have time, Roberto, to give this one here?
Yeah, sure.
Yeah. So the final example I want to give you is some very recent work. We haven't published this yet. On what we call argumentative large language models. That is, of course, a big problem with large language models these days in terms of trusting what they're doing, understanding what they're doing, getting explanations out of them that tells us why certain conclusions are drawn. And this is especially important because they hallucinate. We don't know which information they're drawn from, et cetera, et cetera. So what we started doing, and this is, of course, as I said, we are at the beginning of a path here, is trying to see whether we can use LLMs by picking their brain, but then building debates from their outputs, which are responsible for drawing conclusions, which are by definition faithful because they are done argumentatively. So in a sense, we are using LLMs for providing information, but then we are taking the reasoning out of LLMs and doing it argumentatively. So we have conducted several experiments in comparison with a bunch of baselines, including LLMs and the very popular chain of thought baseline that is very, very broadly used. We've done this work before the latest OpenAI system. But the principle would stay the same. So basically, the baseline would just, in the case of claim verification, would just return a true or false kind of outcome if suitably prompted. And you can ask them for explanation, and they'll come with an explanation. But how do you know that it's faithful to the reasoning? You don't. So there are explanations, but they are unfaithful, most likely. Whereas in our case, we basically prompt LLMs to get arguments for and against the claims, and we can choose how many for, how many against. We can choose how deep the debate should go. And we gauge, we measure the uncertainty of those arguments, for example, by prompting the LLMs themselves. And this leads to bipolar argumentation frameworks, again, to which we can apply one of the gradual semantics and come up with a conclusion, again, true or false, but an explanation which is by definition faithful because it's taken out of the arguments that have been dug out. So we are kind of taking the kind of reasoning out. And this is very competitive with what LLMs are doing in a non-transparent and and kind of magic way. But also, in addition, they are fully contestable. So you can, for example, take some claim, birds are important to badminton, generate attacks and supports, as in this case, and say, okay, by analyzing this attack and support, I draw the conclusion false. You can look at the argument that says, this bit is rubbish. It shouldn't have such a high intrinsic strength, 0.9. The intrinsic strength should be lower, 0.5. And therefore, I can contest the output it gives. It's not false. It should be true. That's all there in the open. You can do it. And you know what to touch. So you can touch the intrinsic strength, and you can also add new arguments. You can come up with your own arguments and somewhat augment, if you like, LLMs with the ability to explain and being contested by this very simple means of redressing. Okay, I managed to come to the end. Takeaway messages are that explainability and contestability are crucial towards trustworthy AI, and computational argumentation can empower various forms of explainability and contestability. Of course, there are lots of things still to do. The neuroargumentative machine learning direction that I've just illustrated with a lot of attention still needs a lot of developing, as does the contestability. And there are various types of computational argumentation frameworks that I haven't discussed, which, however, exist and could be very useful in this context, in particular, those that take into account the probabilistic information and preferences as well. So they actually exist, and it would be interesting to study them in this context. I'm grateful to my sponsors and all my collaborators and my group, and I'm happy to take questions.
Thank you very much, Francesca. Questions? Yeah. Sorry.
Well, I think it's a very interesting work you're going forward with. So I see that all these argumenting and trying to explain the AI is humanly directed. So are you building AIs that are able to contest other AIs? Like making them fight between each other in order to, to see whether the argument is powerful enough? How could you control that? How?
None of these examples did that, but it's a very natural direction to take. And indeed, we are exploring this in the LLM setting. And there is already research that says that if you get LLMs to argue with each other, they can improve. But the arguing they do in the existing work is very unsophisticated. Sorry, I say this arrogantly, being a computational argumentation person. So yeah, we are working in the spectrum. And you're right, both AIs arguing with each other and contesting each other, but also importantly, and that's something that not many people do, we can get AI to help humans by somewhat playing devil's advocate and contesting what the humans are doing, rather than the other way around. So that's another important direction that we are exploring.
And last question, thank you very much. you know, I feel like faithfulness is a little bit contradictory with learning. In the AI, like the condition that you put that the AI has to be faithful to its original premises makes it more difficult now to build an explainable AI. And that's why I say, like, maybe having two models that are faithful to, you know, pro and against. And then, you know, I don't know, it's
So when I
complicated.
talk about faithfulness, the faithfulness is of the explanation to the model. So if I am explaining the way I'm thinking, I try to be faithful to the way I'm thinking. You know, I'm not trying to explain using somebody else's brain. I'm using my own brain. So I need to be faithful to myself. And similarly, when we build explanations for models, we don't want to explain. That's why LLMs, if you ask them, can you explain this output, they would explain. But how do we know that those explanations are faithful to the reasoning they did to come up with the conclusions in the first place? We don't. And actually, they're not, because LLMs are just predicting completions of sentences. Yes. So the faithfulness there is about the explanation versus the actual model. And I think, to me, this is an important prerequisite that we must have.
Yeah, I think I understood it a little bit wrong, the faithfulness concept. Now I see it after you respond, like more of how the model, you know, is like the importance of this particular argument is to the model, or the, you know, the robustness of this particular argument. I see.
Yeah, faithfulness has many names.
Yes.
The people call it also stability. I mean, there are various ways. Robustness is another one. Correctness, there are various names. I like to call it faithfulness.
Yeah, I think it's great.
It's
great.
Yeah.
Thank you.
Thank you.
Okay. Questions? Yeah. Maybe one or two more, and I guess we need to wrap up.
Thank you, Francesca. Very nice, and I, for one, completely agree with what you're trying to do. I'm not an expert, obviously, but I'm curious if in your argumentation, is it able in the end to know if something is a fact or an opinion, or does it take more rounds for it to get there?
Yeah, that's a very important point. Thanks, Sophia. So the intrinsic strength could be one of the tools that we use to distinguish between what's an opinion and what's a fact. I mean, in principle, if something is absolutely a fact, so for example, we can track some information down to a Wikipedia page that we trust completely, then we can say this has an intrinsic strength of 0.99. There is always maybe an element of uncertainty. Whereas if something that we have read in a not so reputable newspaper or on social media, we may say the intrinsic strength of this is extremely low, so it could be very close to zero. So we have that tool, and we can, as we do in the LLM's work, we have ways to measure, in a sense, that intrinsic strength. But in addition, we have the power of debate. So it could be that we believe that something is a fact, okay? So maybe, I read this on Wikipedia, it's a fact. Very high intrinsic strength. And then Roberto comes and says, look, that Wikipedia page is absolute rubbish. They know nothing about quantum computing. And here is another page that says otherwise. Now I have a power to play with the intrinsic strength, but also to add Roberto's argument to my debate that will lower the role that information plays. So we have a lot of tools within computational argumentation for that. And it being non-monotonic means we can change our mind anytime. And we don't care about inconsistency, because argumentation thrives when there are inconsistency. You won't have debate if everybody agrees, right? So it's actually also inconsistency tolerant in a way that other logic-based methods are not. So I don't know whether I directly answered yeah. No, but I think it's a very important point, right? The fact that we can somewhat distinguish and be more fine-grained.
Okay, yeah.
Thank you. So a problem I've seen in dealing with bias in models is that maybe you at some point remove, let's say, gender from your data set, trying to avoid the model to learn some biased relationship. And instead your model learns some surrogate of gender based on height, some other property. Does your approach of contestation and fine-tuning deal with this better? Do you see the same problem?
You're perfectly right, and this is indeed the big problem. So in the approach I have shown you on debiasing, we don't do that, but we do other work that I haven't talked about on what we call argumentative causal discovery. And there we basically perform causal discovery by reasoning with the outcome of statistical tests and some theory of causal theories, which can be written in kind of logic. And there we can see whether there are indirect dependencies, and we can actually contest the information held by playing with the causal graph that we obtain by reasoning with the data. So one of my PhD students have actually is working on this and has integrated the causal discovery with neural networks in a way that allows experts to play with the causal graphs being learned neurally in a way that helps sort out issues such as these. So, I mean, I can say we have answered the problem, but we're definitely working on the problem.
Cool, thank you.
Thank you.
Hey, thanks for the talk. I'm still a bit confused on sort of deeper the network goes, the more difficult it is to find an argument in the network. How do you deal with deeper networks, for example?
Indeed, the techniques that we have developed, the ones I started with, can only cluster within the same layer. So they won't compact layers across. So those ones, but in general, multi-layer perceptrons, if they're useful, you don't need them to be very deep, typically. So that's fine. The problem arises if you have I don't know, transformer-based networks, which are instead very, very deep. So that's an open question, and I'm not so sure as to whether with a really huge size, those techniques would be workable. So you're perfectly correct. What we do with images is instead of deploying exactly this technique to a CNN, which we could do by applying exactly this to the MLP to the fully connected part of the CNN. What we do is we develop new models which are prototypical part-based learning, where we use prototypes drawn from data points and use argumentation to reason with them. And there the depth is not huge. But as far as transformer-based models, we haven't really yet cracked it. Thank you.
Okay, then let's thank Francesca once
Thank
more.
you.